So we continue on curves, parametric curves. So we have been talking about Bezier curves, which are basically the curves which approximate the shape a user wants to design, right. So the way these Bezier curves are defined, you are given these control points B0, B1, B2, B3, right, and all it takes is the blending functions in the form of Bernstein polynomials, and when you take a combination of these control points with these blending functions, it results into B-spline curves, right. So, for this input Bezier polygon, you get a curve like this, right. So, you can see there is a correlation between the shape of the Bezier polygon and the resulting curve shape, right. And we also notice that the degree of the curve, the resulting curve, is directly related to the number of control points we have in the Bezier polygon, right. So, in this case it is a cubic Bezier curve, where the total number of control points in the Bezier polygon is 4, right. So, sometimes it is also referred as the order of the curve as the same as the number of control points. So, the order of the curve is 4, the degree of the curve is 3, right. So, and again so it's just a review what we saw it last time. So, these Bernstein polynomials are basically defined as here, right. So, these are the polynomials in T I and 1 minus T n minus I, and we observe that with the definition J 0 defined at T is taken as 1, J n I T for the rest of the i's belonging other than 0 and n is 0, right, and it sums to 1. All these blending function coefficients sum to 1, okay, between 0 and n, and each of these is actually non-negative, right, for the t parameter spanning between 0 and 1, right. So, these in fact properties of the Bernstein polynomials in turn renders lots of properties for the Bezier curve, which we have seen it last time, right. So, this partitioning of the unity, the convexity of these coefficients, right, all this actually is useful for the properties of the Bezier curve. Okay, so, for a cubic case, this is how the Bernstein polynomials look like, right. And when you see the curve, is basically a combination of these coefficients with the respective Bezier points you have, right. It is just a combination of that. So, this definition is somewhat similar to what we also have observed in the cubic splines, where we see the resulting curve as a combination or blending of the geometric information given. So, here the geometric information is basically given through the control points of the Bezier polygon, right. That is what you are trying to blend with using Bernstein polynomials, right. So, this was basically using the Bernstein polynomial. So, these are some of the examples which we saw. So, here it all shows that the shape of the Bernstein, the shape of the Bezier polygon is actually directly influencing the resulting curve, right. Okay. So, then we actually started looking at a different way of constructing these Bezier curves, right. So, one was using Bernstein polynomials just as a basis or blending function, and there is another way of constructing these Bezier polygons, and that is due to this de Castelot algorithm. So, de Castelot algorithm basically works using linear interpolation. Okay. So, the idea there is that if I have the parameter defined, let us say between 0 and 1, the parameter t is defined. So, for any value of t, I can locate a point on the curve by successive application of linear interpolations. So, that is the underlying idea about this algorithm, which basically means that if I apply a linear interpolation onto the leg or the span of the Bezier polygon, let us say for this leg I apply this linear interpolation to get the point B10 somewhere there. Similarly, for this span I apply the linear interpolation and obtain the point B11, and then subsequently I get a new span defined between B10 and B11, right, and I repeat the linear interpolation for the parameter value t along this span and get the point B20, right. So, this B20 is nothing but again a linear interpolation of B10 and B11, right. And if I just expand this, because B10 was nothing but a consequence of linear interpolation in the Bezier polygon, and B11 was also a linear interpolation. So, if I just expand this, I obtain this, right, 1 minus t square B0 plus 2 t minus 1 B1 plus t square B2, right. And this is nothing but, these are nothing but the Bernstein polynomial coefficients, right, of degree 2, right. So, all it does is, with this application of linear interpolation on this span, it locates a point B20, which is a point on the curve, right. So, for any value of t, I can locate the point on the curve by successive application of linear interpolation, right. That is what de Castelot algorithm is, right. So, the way I can sort of extend, that was the example which was given for a quadratic Bezier curve of degree 2, but this can be extended to any degree, right. And all it looks like is some sort of a recursive formulation here, right. So, given the Bezier control points at B0 to Bn, I obtain at some level, let us say rth level, the points Bri, which are nothing but the linear interpolation of the points which are obtained in the previous level or the previous iteration, right, which is r minus 1, right, and I keep applying that till this r equals to n, right. So, that is the algorithm I have for any degree of the curve, right. And given that the first level where I start, these are the points of the Bezier polygon itself, right. So, if you look at the way this computation is going on in the case of the example of a cubic curve, so you observe that you have some sort of a triangular array which is being formed, right. So, this and this gives you this and so on, right. So, all you see is basically a triangular array which is being formed, right. So, there should be arrow from here also, there should be arrow from here also, right, if you want to see the computation which is going on. Right. Here all it is being shown is the storage or the array which is formed at different levels. Fine. Okay. So, having seen this, let us try to look at some of the properties which we have already studied, but using Bernstein polynomial construction. Right. So, how are these property revealed when we have T-Castleau algorithm construction? Okay. So, we just sort of revisit these properties, some of them. So, we remember that affine invariance was basically a property where it was equivalent if I apply an affine transformation to the curve, or if I apply the affine transformation to the Bezier polygon or the control points, right. So, if I apply affine transformation to these Bezier polygon points, then the curve computed is the same as if I had applied that affine transformation to the curve itself, right. So, these are two equivalent. So, how do we see that in the formulation using T-Castleau algorithm? It is actually from the direct consequence of the algorithm itself. Why? Because T-Castleau algorithm is employing linear interpolations. And what are linear interpolations? These are just the affine maps, right. So, just the fact that it is actually a sequence of linear interpolation, which is what is being used in T-Castleau algorithm, this is a direct consequence. Affine invariance is a direct consequence, right. Linear interpolation uses just the ratios, and that is what affine maps are, right. So, this property of affine invariance is inherent to the algorithm itself. Right. Now, what happens, let us say, if I am talking about projective invariance? So, are Bezier curves invariant to projective transformation? Are they? So, you understand what projective invariance means? So, see here what we have done, we have applied affine transformation, right, and we observed that there is no difference if I had applied to the Bezier polygon or to the curve, right. These are the two same things. Now, if I apply a projective transformation, now that you know what projective transformation is, would I have got the same result? That is the question. That means, if I apply projective transformation to the Bezier polygon and obtain the curve, or I straight away apply the projective transformation to the curve, are these two the same? The answer is no. Okay. So, we will see that some of the curves can be made projective transformation invariant at a later stage, right. So, the Bezier curves are not projectively invariant. Okay. Now, the other property which we looked at was the convex hull property, right. So, the convex hull property said that the curve which gets formed resides inside the convex hull of the control polygon. Right. This was the convex hull property, right. And due to the nature of the Bernstein coefficients, they being non-negative and summing to 1, this property was easy to observe in that formulation. Now, let us try to see the same thing in Decastleau algorithm formulation, right. So, once again, if we just look at the construction mechanism, which is to use successive application of linear interpolation, right. So, what do I have is, this is the definition of the curve, right. This B n 0 t finally gives me the curve P t, right. And if I observe that each of these intermediate points which I obtain after applying the linear interpolation are nothing but convex combination of the previous points, right, of the level r minus 1, right. Convex combination meaning because I am just using linear interpolation, 1 minus t and t, right. So, again this successive application of linear interpolation would result all the points which are getting computed to reside in the convex hull, right. So, again this is inherent to the method of using linear interpolation, right. Okay, so, next the other properties like endpoint interpolation is also fairly easy to observe, because if I just look at the point evaluation of B n 0 at t is equal to 0 is nothing but B 0, which is the first control point of the Bezier polygon, and similarly the evaluation at t is equal to 1 is the last Bezier point, which is B n. Okay, so, this is also fairly easy to observe. And if you look at again the parameter transformation, that means instead of having the definition t defined in the span 0 and 1, if I have a parameter u defined in an interval a and b, right, it does not really change, the method or the algorithm. All I need to do is make this a fine transformation of the parameter, right, obtain t as nothing but the ratio of u minus a to b minus a, right. So, most of the properties which we looked at in the case of Bernstein polynomial formulation can also be observed and asserted using Decastleau algorithm, right. Now, let us try to see some more properties of Bezier curve in general. Okay. So, now let us say we are considering a scenario where we want to have a definition of one Bezier curve, right, defined as from B 0, B 1, B 2 and B 3. So, this defines a curve P 1 t, this is one Bezier curve, and I have another curve defined using set of control points as C 0, C 1, C 2, C 3. Okay, which is P 2 t, right. Now, if I am talking about the continuity at the junction point of these two curves, right. So, first thing I can look at is the positional continuity, where the first point of the second curve should match with the last point of the first curve, right, because that is the minimum requirement of the two curves to be joined, right. So, we are talking about positional continuity, right. So, that is what we call it as C0 continuity. Okay. Right, this is the first curve.
The 4 control points for the second curve.
Right.
Now, a joint curve, does it mean that it's got to be, are you saying continuous at this point, or is it the curve that is formed by these 8 control points?
No, we are not looking at a new construction. So, we are basically joining two curves, right. So, this is a cubic Bezier curve, this is another cubic Bezier curve, right. And so, if I have to define a joining here, right. So, how can I define various kinds of joining looking at the desirable continuity I have, right. So, if I have to design the two curves which have just the positional continuity, then I can place any way I want these 4 points, right. But if I have, let us say, higher order of continuity, then I need to do something else, right. So, this is the minimal configuration of joining at this point, which is to ascertain only the positional continuity, right. So, clearly when I see the effect of this, I have this curve, another curve, right. So, I see some sort of a sharp change here, which does not look smooth, right. So, here again I am talking smoothness in terms of visual sense, right. So, the curve does not look smooth. Okay. So, now let us say if I want to make this curve look smooth, I need higher order of continuity, right. That means, so here we had considered only the positional continuity, then we have to perhaps look at the derivatives, right, the continuity in derivatives. So, that is what gives us the C1 continuity, where I look at the continuity in terms of the first derivative of the curve, right. So, here again if I have, let us say, the first curve defined through the Bezier polygon B0, B1, B2, B3, and the second curve C0, C1, C2, C3, then here if you look, it looks smoother, right. The transition from one curve to the other curve is smoother, and in order to establish this, I would require the condition being satisfied that the first derivative at the last point of the curve should be the same as the first derivative at the first point of the curve, right. And if you go back and look how we found out the derivatives of the curve and do the evaluation at t is equal to 1 for the first curve and at t is equal to 0 for the second curve, would in turn give you a relationship between the control points of the two Bezier curves, right. And in fact, for the first derivative, you remember that it was just the first and the last spans of the polygon, right. These were the derivatives. So, that is what is being used here. This is the last span of the first Bezier curve, and this is the first span of the second curve. So, this would give me the desirable location for the control point C1. Remember, if I am talking about C1 continuity, it already uses C0 continuity, right. So, I have already established that C0 is the same as B3, right. So, for the purpose of designing the C1 continuous curve, the question becomes where do I locate C1 point, right, and that is what I obtain using this condition, right. So, this is how I get a curve which is C1 continuous. It is all through, right, it is all through. See, the continuity is being evaluated at the junction point, right, but this is actually, if you look at the differentiability of this with respect to t, is continuous. So is here. Yeah, they can be anywhere. So right now the only constraint which has been imposed is for C1, right, which necessitates to locate the point C1, and as long as the C2 and the C3 points are concerned, you could locate anywhere you want, depending on what kind of shape you are looking at, right. Okay. So, now let us say one level more, let us say I want to have C2 continuous, which would require continuity in second derivative, right. So, again if I do the evaluation of the second derivative for the two curves and do the evaluation at the last point of the first curve and the first point of the second curve, I would basically get a relationship of the relevant control points on the two sides, right. So, now again given the fact that C2 continuous curve is going to be C1 and C0 continuous, I already know certain information about, let us say, the point C0 and C1, they have already been located, satisfying those conditions, right. So, using that I can evaluate C2, right. So, now you see that C2 is given as B1 minus 4 times B2 minus B3, okay, because C0 is B3 and again C1 minus C0 is the same as B3 minus B2. So, that gives you C1, right. So, you just use that information to get C2, right. So, how does it look visually? Now, I have the first curve P1t given as this through B0, B1, B2, B3 and the second curve given as P2 through C0, C1, C2, C3, right. So, now, if you look at the relationship of the control points in the two curves, so C0 is the same as B3, satisfying C naught continuity, and C1 minus C0 is equal to B3 minus B2. So, basically all it says geometrically, if you want to see that this leg of the polygon in the first case is the same as this leg of the polygon and they are collinear, right. Now, whereas if you see here C2, the evaluation of C2 can also be written as C2 minus B1 as 4 times B3 minus B2, just rewrite what we have obtained earlier from C2, right. So, what does it say? That C2 minus B1, if you just look at it as a vector, is parallel to B3 minus B2, or all these 4 points are sort of, actually 5 points are collinear, this, this. That is also a possible scenario in order to have this curve to be C2 continuous. So, what you observe here is that if I join this line here, right, this is parallel to this, right. So, this is how you can obtain a C2 continuous curve. Of course, from the user's perspective, when you are designing curves, it is going to impose constraints where you can locate these points, right. So, that takes away the flexibility of positioning these Bezier points, right. So, for most practical purposes, people actually just want to design C1 continuous curve. Right. There is another type of continuity, which is, if I let us say go back to the C1 continuity. So, here again for a C1 continuous, if you want to look at geometrically, this leg is the same as this leg, right, both in direction and size, right. But if I had the two legs collinear, but not necessarily of the same magnitude, right. That means, this leg could be longer, let us say go here. Then again I would see the curve would look smooth as far as the visual sense is concerned. Okay. So, at times we call that as visual continuity or geometric continuity, G1, instead of calling as C1, call that as G1. So, all we are concerned there is of the direction and not necessarily of the magnitude. Okay. So, this is just a variation of C1 continuity. Okay. So, now going to another let us say feature of these Bezier curves is that even for the purpose of facilitating the design of the curves, as we observe that the degree of the curve is basically defined by the number of control points we have, right, and control points are the control handles for designing the shape of the curve. Right. I can displace those points wherever I want, and larger is the number of control points, more is the control I have onto the shape of the curve, right. So, at times what may be desirable is that I construct a curve of a certain degree, right, let us say cubic, which has 4 control points, and suddenly I feel that I should have one more control point, because that will help me changing the shape or redesign the curve, right. So, additional control point basically implies changing the degree of the curve, because the degree of the curve is directly related to the number of control points I have, right. So, if I am trying to change the control points, if I want to increase the control points, I am basically implying that there is an elevation of the degree of the curve, right. So, this could be useful in certain scenarios, right, even in the case of let us say joining two curves. What I may do is I may match first the degree of the two curves, and in order that I match the degree of the two curves, I may have to elevate the degree of one of the curves, right. So, there could be various scenarios where we may use this feature. So, what are we saying here? That we increase the degree of the curve, which basically implies increasing the number of control points of the Bezier polygon, right. So, if I have let us say curve defined through the Bezier points B0 to Bn, right, now I am getting a different set of control points as B 0 star to B n plus 1 star. Right. So, all we are saying is that first I want to have the same curve. Remember that the same curve defined using a different set of control points with elevated degree. Right. I am not changing the definition or the shape of the curve. Right. For the given configuration, I just want to have the degree elevated, right, which basically means that these two curves, the curves obtained using this set of control points and the curve obtained using this set of control points should be the same as far as the curve is concerned. Right. So, which basically means that I have this curve through these points, this curve through these points, and I have these curves same. And what I am trying to do here, I already have this, right, this left hand side. I am trying to locate these B stars. What is the set of new control points with an elevated degree for the same curve? Right. So, I just basically establish this relation to obtain the B I stars. Fine. Okay. So, how do we sort of proceed? I equate these, right, and I expand the terms for these polynomials here, right, and then in order to be able to get the coefficients B I star, I need to have the same degree here, right. So, what do I do?
Equate the coefficients having same degree of t.
Right, but I have to first of all make this degree high, right. So, I have to use some trick. So, yeah, multiply by unity, right, and that should contain t's and whatever I need, right. So, I use this identity t plus 1 minus t, which is equal to 1, and multiply the left hand side with this, right. And now I can equate coefficients of the two sides of say t to the I 1 minus t to the n plus 1 minus I, right. So, if I compare the coefficients on the two sides of t to the I n 1 minus t to the n plus 1 minus I, this is what I get, right. Now, further simplifying this actually gives me these B I stars as nothing but I over n plus 1 times B I minus 1 minus I over n plus 1 times B i's, right, which is nothing but some sort of a linear combination of these Bezier points B I minus 1 and B I, right. So, if I use a parameter like alpha equals to I over n plus 1, this is just a linear combination using the parameter alpha, right. So, just observe an example here. Let us say I have a curve defined through these control points B 0, B 1, B 2, B 3. So, again this is a hand drawn curve. So, you should not see this to be an exact curve, right. So, the exact computed curve may look like different. So, now if I want to elevate the degree of this curve using the same result which we had would basically give me these B stars, right. So, this point will be some linear interpolation by 1 by 4 using, right. This is by half and this is by 3 by 4, right, or whatever I over n plus 1 we are saying, right. Right. So, this basically does the localization of the B stars, right, for the same curve, and obviously, the first and the last points have to be the same, right. Okay, now tell me what happens if I do this degree elevation repeatedly. Let's see, from here I can go further, right. I have elevated the degree from 3 to 4. Now, I do a next elevation and next elevation and next elevation. It will converge to the curve. Right. You can actually prove mathematically also. Okay, so now we see a sort of a
We had earlier studied about having cubic spins. There I read that increasing the degree leads to the curve woggling more.
right.
So what does that mean?
See, is basically
Lesser, and it also said it means lesser control. Hence we go ahead with cubic splines in the normal cases. That was the question, like why we use cubic splines. So
right. So, see, there we are trying to do an interpolation of set of points, right, and if I try to have the degree as the same as the number of points, that is a typical scenario, then I will have wiggliness, control points, the number of points which I am trying to interpolate. See, often that is what the case you will have in Lagrange interpolation, you know that. So, you have a very high degree of the curve which you obtain. So, this is not the same type. See, it is not an interpolation here, right. But of course, there are other issues related to elevating a degree, right. First of all, the moment you increase the degree of the curve, computation is an issue, right. So, the simplicity is going away, right. But from the purpose of the design of the shape of the curve, you have better control, because you just have more number of points to move, right. Right. And remember that we have the property of something like pseudo control, right. So, the pseudo control gets more, let us say, influenced by adding more number of points, right, because you are sort of distributing that influence. If I had just a cubic curve, if I displace one point, it will affect a larger range of the parameter, right. If I have additional points, so the range, the same, for the same effect, the range is going to be smaller, right. Okay. Another question I have is, let us say we have talked about degree elevation, right, where we were trying to increase the degree of the curve. So, can we also think of reducing the degree of the curve?
not reduce it below.
So, see, the problem becomes is that reducing the degree means what? Reducing the number of control points, right? And of course, retaining the necessary properties of the curve, right. So, it actually turns out that it is not always possible. You might be able to do it only for certain situations, right. For instance, here I can do the reverse construction. From here I go and obtain this, from here I go obtain this, but not always.
So, but not always or but not beyond that.
Not beyond that.
There are two separate things.
Yeah, right. Okay. Fine. So, now we take another sort of a property or a feature of the Bezier curves, which is the subdivision of the curve, right. So, what do I mean by subdivision of the curve is, let us say I want to divide in two parts, and when I say two parts, I am basically referring to the range of the parameter, right. So, this curve, let us say P t defined between 0 and 1, and I define another set of two curves, let us say Q u and R v, which are individually defined in the unit interval for the parameter, whereas this actually is referring to a curve up to t is equal to 1 by half 1 by 2, and this R v is referring to the other half, right. Okay. So, basically here if you look at this curve, I am trying to divide this curve into this Q u and R v, right. That is what the problem is. Any suggestions? Okay. Let me give you some hint there. So, if you recall recast flow algorithm, right. So, here is this point, right. This was the point where the subdivision was to take place, right. So, the left side I needed set of control points which could define this curve, and I needed another set of control points which could define this curve, right. That is what it implied, subdivision of the curve, right. So, now if I consider the evaluation of the curve at t is equal to half, right, 1 by 2, and if I see the construction from recast flow algorithm, this is the point which gets located on the curve for the evaluation t is equal to 1 by 2, right. And the other points which I obtained from the previous iterations of the recast flow algorithm can actually act as the control points. See, if I do a recast flow algorithm t is equal to half, this will get located here, this point gets located there, and this point gets located there, right. And further application gives me the point here, the point here, right. Once more application gives me the point on the curve, right. And this is the point where I am taking place this subdivision, that is where I am subdividing the curve. So, now if I see this point and this point, of course, these points, they define a set of control points for this curve. Okay. And similarly, this and these two endpoints define the control points for this part of the curve, right. So, the proof of this is a little involving, but you can try. Okay. Now, again let us say if I have to do a repeated subdivision, I will converge to the curve. Right. So, this is like some sort of a corner cutting when you look at the way Decastro algorithm is working, like this corner is cut, this corner is cut, right. In the subsequent subdivision there will be another corner cut of these, right, and eventually I will get the curve, right. So, it says that if I have a polygon and I just keep chopping these corners whenever they get built, ultimately I will get a smooth curve there. So, it sort of intuitively matches with what we see as a corner cutting, right. Okay. So, so this is the sort of result we have for the subdivision. So, now we have covered most of the aspects of Bezier curve. So, this is just to motivate to do something else, understanding the limitation of the Bezier curve, right. So, if we look at Bezier curves, what we figure out that as far as the local control is concerned is limited, right. There is this pseudo local control we have, but a change in the position of a point in the Bezier polygon results change in the entire curve, right, which is sort of a global effect, and it may not be a very convenient way of designing larger free form curves. Exact local control I would basically mean that if I have let us say if I go back here, let us say a curve defined in this fashion, and if I move this point, right, I observe that the entire curve changes, right. What I may just want that only part of this curve changes rather than the entire curve, right. So, there is a sort of a range of influence with respect to this point. It is there in some form, but it's actually every point of the curve changes. So, I cannot do away not computing those points, right. As far as the curve is concerned, I have to do a recomputation of the entire curve, right. Okay. So, one thing is that we have no local control, or let us say limited local control, right. And the other thing is that the degree of the curve is fixed by the number of points I have in the control polygon, right, and that may again be an issue for various applications. So, it may be nicer to have a decoupling of the control points I use for the gross shape of the curve and the degree of the curve which I design, right. So, these limitations are overcome in B splines. Okay, so, that is what we will do next time. Okay. Thank you.